Um, yeah, okay. Recording. All right. Hi. Welcome to Wednesday. Um, Reminder, I guess, that the final exam is being released today. I plan on releasing that right after class. Um, it is due ostensibly on before like 11:59 p.m. on Friday, which gives you um well, okay, here's the thing. After looking it over last night, I do think that it might. I'll give everyone until noon Eastern on Saturday to complete it, so an extra 12 hours, which means that you should have just over 4 days um, to complete the final. Uh, so yeah, it is again 65 points. It's going to be worth 50 points, so you can get up to 130%, or you could see that as you don't have to complete the entire final to get 100%. Um, I'll make a post on Piazza with all of this uh, information. I guess it doesn't really make sense to give a bunch of course announcements to just the two of you, so it's fine. Um, PA6 is due, uh, or sorry, problem set 6 is due um, on on Friday as well. So if you haven't looked at that already, make sure to take a look at that. That is entirely extra credit. Uh, and of course, Project 3 is due tonight, but if you have late days available, you can turn it in late. Okay. Um, any questions about any of that before we get started? Nope. All right, cool. Okay. Any last minute questions about content from the course before we get started? I guess technically the final isn't out yet, so if you have questions about stuff that might be on the final, I can try to answer those now. One, yes, okay, perfect. What is it? Both DFS and BFS have the same time complexity? Yes. They both have um, V plus E, theta V plus E. Okay, if there's nothing else, um, I guess let's keep talking about max flow min cut. Okay, so if you remember from yesterday's lecture, um, the max flow and min cut problems were a pair of sort of dual problems on a graph. Um, the layout for which is we have a source vertex, and then we have a bunch of things. Um, and then we have a target vertex, right? And we have capacities along all of these edges, so we have like weights along all of these edges. This was not the same graph as last time, but it's a graph nonetheless, and that's what matters. Okay, so if you remember, a flow is um, a like or maybe an ST flow. We think of the edge weights as capacities. And push stuff from S to T without exceeding the capacities, right? Um, so we think of this edge as like a wire that can hold 5 units of flow, like 5 amps of current or whatever. Um, and uh, we we sort of think of S as a source, T as a target or as a sink, and we kind of we push current from S to T, right? So maybe we put 3 amps along this path. We can't put any more than that because it crosses this edge, and this edge can only hold 3, right? So that's kind of, yeah. Um, we can push one more this way, right? Uh, and so the idea of a maximal flow or the value of a flow um, is the total amount being pushed from S to T. Right. So the max flow problem asks us to find a flow with maximal value. Right. So that's max flow. Min cut you can think of as a dual problem to this. So maybe I'll I'll write it here. So or maybe I'll say a cut. For cut, we remove some edges to disconnect S from T. Right. So we're sort of cutting the graph, right? Or you could think about cutting it here, or you could think about cutting it like that, right? You can cut it any number of ways. Cut it like this, right? So remove some edges that disconnect S from T, and um, a min cut is uh, find a cut with minimal weight. Or here, weight refers to the sum of the weights of the edges that we're cutting, right? This is all stuff that I gave more precise definitions of yesterday, but hopefully, hopefully this quick refresher makes sense. Then yesterday we stated a theorem, which I did not prove, and I will continue to not prove. Um, but maybe I'll give you some intuition for it, or maybe what we talk about today will give you some intuition for it. Um, the value of a maximal flow is always the same as the weight of a min cut, right? Um, I guess for a bit of intuition, um, a cut represents like a bottleneck from S to T, right? So for example, I think the minimum cut here that we can make is cutting this 3-in-1, right? And because like every path from S to T has to go through one of the edges along the cut, right? Which means that if the total weight of the cut is here, it's 4, right? Um, then the most amount of stuff that can go from S to T at any given point in time is 4, right? So maybe it's sort of clear that the value of a max flow is always like less than or equal to the weight of the min cut, right? It can't possibly be greater because if it was, then we would be overwhelming the capacity of the edges along the cut somehow, right? So I guess the key like statement or the interesting statement of the theorem is that you can always achieve the min cut as a maximal flow, right? You can always do at least as good as the min cut, right? It gives you the greater than or equal to part of that. Um, okay, so like I said, I'm not gonna I'm not gonna talk too much about proving that, but I will now describe an algorithm. Or I guess before I do that, does the idea of a max flow and a min cut make sense? Sort of like intuitively, you can you conceptualize that? Yes. Okay. Yes. Perfect. All right. So I'm going to talk about something called the Ford-Fulkerson algorithm. Oops, I did not post yesterday's lecture. I will post that. Uh, yeah. Okay. So Ford-Fulkerson is an algorithm that um, takes a weighted, directed, connected graph and a pair ST and produces a maximal flow from S to T, right? So uh, I'll say maybe algorithm for finding max flow. Okay, so it's a greedy algorithm for starters, right? Which, if you remember from like Monday or whatever, means that there's some kind of matroid hidden here, right? Um, the uh, I think the tricky part of defining the matroid is um, the sort of the third like exchange rule, and I think that ends up being like taking two paths that go from S to T and exchanging an edge from one path to another, or something like that. But I could be wrong. But anyway, it's a greedy algorithm. It starts by finding um, it works on the basis of these things called augmenting paths. Right. So the at a high level, the way the algorithm works is we say while there is an augmenting path from S to T, we add as much flow as we can along that path. right? Um, I'll define augmenting path. But it's greedy in the sense that we don't ever like we never explicitly backtrack. We never explicitly think about the fact that, oh, maybe I shouldn't add flow along this path because doing this would sort of lock me out from doing something better later on, right? We just kind of we find a path and so we push as much flow as we can. When I say as much flow as we can, what I mean is uh like suppose we find this path here, right? 1, 2, 6. The maximum capacity of this path is the minimum capacity of any edge along that path, which is 1. So we push 1 unit of flow along everything here, right? If we find this path instead, the the max amount of flow that we can push is 3. So we push 3 units of flow along here, right? And so we find an augmenting path. We add as much flow as we can along that path. We find another augmenting path. Add as much flow as we can, and sort of keep doing this until there aren't any more pads. Now the cool part here is, or what I think is a cool part of this algorithm is this idea of an augmenting path, because the definition kind of bakes in a sort of um, it lets us be greedy while at the same time accounting for mistakes that we may have made, right? So it's like greedy without being greedy, right? So augmenting paths kind of let us backtrack a little bit. Did I misspell? Oh, there we go. Okay. So let me define this. Um, I will start by redrawing the graph from before. And then I think I had an edge going up here. Yeah. Okay. It was this 5, 1, 3, 2, 4, 6, 2. Okay. 2, 4, 6, 2. Okay, so the first thing we do is add sort of residual edges, right? So here's our original graph, right? We add these like fake virtual edges to the graph that go backwards. So for every edge, we add an edge that goes backwards. So we've got something like this. And we set the capacity of each of these edges to 0, right? Now the idea is um, our augmenting path can contain not only proper like forward edges that were originally in the graph, but it can also contain these like backwards edges if we want it to, right? Or we are allowed to find a path that contains one of these backwards edges, right? Um, as long as there's like a positive weight here, right? And pushing flow along a backwards edge like this is basically going to represent um, reducing the amount of flow along the forward edge, right? So I start by finding, um, and so I guess the thing you do is you find an augmenting path. So uh, now we'll say find a path from S to T that potentially includes the residual edges, right? Um, push as much flow as possible along this path. And now we update the capacities of residual edges to just equal. So the capacity of the residual edge is always just the flow along the corresponding forward edge. Right. So if there's only like if this edge, which has a capacity of 2, only has a flow of 1, then there's no possible way that we can remove more than 1 unit of flow, right? So that means this residual edge has to have a capacity of 1, right? Same thing, like here, if we've only got 3 units pushing out here, then we can only have 3 units coming back here. Like we can't reduce it by 4, for example, right? So that's the setup. How do we find a path? Well, here you can just sort of use BFS or something, right? This doesn't have to be a shortest path, right? This can just be any path, right? So we can just like start, we can kind of explore out until we find a path that works and then push flow along that path. We don't need to like we don't need to pick the best one or anything. Um, and again, the reason this works, the reason that we don't have to worry about like making the reason we don't have to worry about like finding a stupid path and then kind of like locking ourselves out of doing anything better is because the next path we find can always undo one of those edges if we need it to, right? Um, so I think in this, if we sort of try to run the algorithm here, um, we start, we push. I mean, maybe we find this as a path, right? The only path we're going to find right now is not going to contain any residual edges because they're all sort of going backwards and they all have a capacity of 0. But we find this path, and so this is an augmenting path. So I'm going to push 1 unit of flow, right? So I'm going to write the flow in green. Right, so I've got 1 unit here, 1 unit along the edge with capacity 2, and 1 unit along the edge with capacity 6. This also means that I can update the capacities of the corresponding residual edges to be 1. Now I can look for another path. Maybe I find this path. Right. I'm intentionally being kind of dense here just to sort of show the fact that we have a residual that our path can include a residual edge. Right. Um, and sort of what happens if we take that residual edge. So well, okay, so first of all, right, this currently the state of this graph is a valid flow, right? There's one unit of flow going here. If I now take this sort of weird path, right? The capacity of this path is also 1 because it's constrained by the capacity of the residual edge. So I can go ahead and push 1 unit of flow along that path, right? 1 here, 1 here, 1 here, 1 here, and 1 here. Now I do my updates. So because I'm pushing a unit of flow along a residual edge, right, that corresponds to reducing the flow on the actual edge. So now I'm going to replace this with 0, and I'm going to update my residual edge to have a capacity of 0, right? And then update the rest of these to have a capacity of 1, 1, and 1, right? So we've done this weird thing where we've sort of like jumped from point to point, right? Um, but you'll notice what we have is still a perfectly valid flow, right? What we have right now is a path like this with 1 unit of flow and a path like this with 1 unit of flow, right? Now we can happily find this path, right? And push 2 units of flow. Oh, wait, I need to update this one as well. Here's 1. Okay, perfect. Now we can find this path if we want, right? And the maximum that we can push through it is constrained by this edge, so we can push an additional 2 units because this already has one unit of flow going. So we'll set it to 3, right? 3, 3, set the residual capacities to 3, 3, 3. And now we can't find any more pads, right? There's no like we could do a BFS starting here, right? We can take this edge. We can't take this edge because it's already at capacity, right? So we can take this edge. We could take this edge back, but that won't get us anywhere. Okay, we could take this edge. Well, actually, we can't take this edge because this is also full, right? So the only sort of like available thing that we have now is this little cycle, right? Everything else is full, right? So there are no more pads. Even if we include residual edges, there's no more pads from S to T. And so we know we're done, right? Um, does that make sense? I know I kind of just talked for a bit. You think so? Um, we have time, so I can like clarify parts of this. Or I can like go over this again, or go over maybe a different example. Let me find a good. Um, I'm just looking online to find a graph that's maybe a bit more interesting. Um, okay, here we go. I'll draw out this graph, and then maybe you all can help me find residual pads, or sorry, augmenting pads. I've got a source. I've got this. Now I'm going to have an edge going up. I'm going to have a nice square like this. Another edge going up, one going diagonal, and then I'm going to have my target. right? So this is very similar to the graph before, but now there's these vertical edges as well. And let me give these edges capacities. So 7, 4. I'm literally just copying this off of um, uh, Google Images. So 5. Oh, this one, it wants to go down the other way. Who am I to argue? 3, 2, 3, 8, and 5. Okay, perfectly good graph. Maybe I'll name these vertices A, B, C, and D. Right. Um, okay, so here's my graph. I'm gonna start by adding in the residual edges, right? Actually, do I need to draw these? Can we pretend that we know that they're there? Maybe it's worth drawing them anyways. Oh, okay. Yes, we can. Okay, perfect. I think the graph would get very cluttered. Um, okay, so I'll start by maybe also writing the current flow that we have in orange, and then we know that the capacity of any residual edge is going to be equal to the current flow, right? So okay, so let's start by finding an augmenting path, right? One of you want to shout out a path from S to T? Any path. It doesn't have to be a particularly clever one. S A B T. S A B T. Okay, this is a perfectly good path. How much flow can we push along this path? 5 units, perfect. Okay, so let's push 5 units, right? So 5, 5, and 5. All right. Any other paths? S A C T, S A C T. Okay. How much flow can we push along this path? 2 more. Yep. So I'll push an additional 2. This goes to 7. This goes to 2. This goes to 2. Are there any more paths? SDCT. Okay. So SDCT. We can push an additional 2. Okay. So 2, 2, and this becomes a 4. Is there anything else? SDACT. Okay. SDACT. How much can we push there? 1. Okay. So S to D becomes 3. D to A becomes 1. A to C becomes 3. And then C to T becomes 5. Okay. Any others? You think there's a bottleneck going from AD to BC? Yeah, exactly, right? So you'll notice that this edge is saturated, this edge is saturated, and this edge is saturated. So when we're searching for an augmenting path, our path can't use these three edges. So if we remove these, if we cut them out, um, S and T are now disconnected, right? So we know that we're done. We know that there's no more augmenting paths. What's the value of this flow? N, exactly, right? I can say, 7 plus 3 leaving S, 5 plus 3 plus 2 crossing this bridge, and 5 plus 5 entering T. It's 10 no matter what. Um, and what's the so if the value of the flow is 10, what's the minimum weight of a cut? Or what's the weight of a minimum cut? According to the theorem? Ten. Yeah, right. It's always the same. In particular, running this um, algorithm, running Ford-Fulkerson, has given us a maximal flow, but it's also told us that the flow is sort of constrained by this edge, and this edge, right? And so uh, these represent, as Tushar said, these represent a bottleneck, and in particular, these represent the minimum cut, right? So after running Ford-Fulkerson, the set of all saturated edges gives us a min cut, right? Where by saturated, of course, I mean an edge that has all of its capacity accounted for, right? So like, or a set of saturated edges, maybe not the set of saturated edges, because the seven is also saturated. But maybe what I want to say is min cut consists of saturated edges, right? Because this represents the bottleneck. Um, does that make sense? Cool. Okay. Um, in the, I guess, 18 minutes that remain, I want to give an application of this to bipartite matching. So I'm going to quickly describe another graph problem. Well, first I'm going to define bipartite graphs. Actually, okay, I'm gonna take a long detour of definitions, is what I'm gonna do. So, uh, a coloring of a graph um, is an assignment uh, maybe um is yeah, okay, it's a function. I'll call it C from V to some set S, um, where S is a set of colors, right? These can be actual colors, red, blue, green, whatever. They can be numbers, they can be whatever. They're just values, right? Um, so a coloring is an assignment of a color to each vertex, such that for every edge U to V in E, the color associated to U is different from the color associated to V, right? So in other words, we color vertices so that no two adjacent vertices have the same color, right? You can think of this as like if you have a map, not I mean, like a physical map. Um, right? Maybe it's got like states on it, whatever, right? You'll see maps like colored in, or like you'll see the states colored in different colors, so that adjacent things are never the same color, so you can sort of like see the boundaries, right? So maybe this is red, maybe this is uh, blue, this is green, which means this has to be red, this has to be blue, uh, this has to be red, this has to be green, this one has to be yellow, this one can be red, maybe we make this one green, and we make this one blue, right? So um, the way that I've chosen to assign colors here, it was not possible to do this with only three colors. We needed a fourth one because this um, this state neighbors a red state, a blue state, and a green state. So it has to have a color that's not one of those three. Um, but you can think of this as a graph coloring problem, or you can think of this map as a graph by giving each state its own vertex, right? And then having there be an edge whenever two states are adjacent, or whenever they share a border, right? So maybe I've got like this one here, this one is here, this one is here. This one shares a border with both of these, so I'll draw one here. It also shares a border with this first state. Wait, no, it doesn't. Oh yeah, this one is here. Um, this one shares a border with uh, this and this, which means this and this. So we add another vertex like that, and so on, right? And now we can think of like assigning colors to the vertices in this graph, um, such that adjacent vertices are never the same color, right? And that corresponds to like uh, states that share a border aren't colored the same. Anyway, that's the idea of graph coloring. I will later talk about algorithms for graph coloring, but for now, I want to give another definition. A k-colorable graph is a graph that can be colored with k colors. And then a bipartite graph is a two-colorable graph, right? So for an example of a bipartite graph, let's say we have this cycle of 6 vertices, right? This is two-colorable because I can make these 3 red, and I can make these 3 blue, right? This is a perfectly valid coloring because any edge necessarily goes between a red and a blue vertex. Um, and it's a two coloring because I'm only using 2 colors, right? You might see bipartite graphs drawn a bit more suggestively like this. So we'll put all the red vertices on one side, all the blue vertices on another side, and then kind of have all of the edges go from like one side to the other, right? So maybe now I've got an edge like that. Right. This is still exactly the same graph. It's still a cycle of length 6, right? 1, 2, 3, 4, 5, 6. But now all of the reds are sort of, oh, that's not what I wanted. What are you doing? Stop it. Boy. Okay. All of the reds are on the left, and all of the blues are on the right. Okay. Um, you can think of bipartite graphs as, I mean, bipartite graphs are very useful for modeling certain kinds of situations, right? So maybe you've got a bunch of students applying for internships, right? And um, you want to know like who applied to what internship, right? So you could have all of the vertices on the left represent students, and all of the vertices on the right represent internships. And then you have an edge from a student to an internship whenever they apply to that internship, for example, right? So like you can have a graph where the vertices don't necessarily all represent the same thing. Um, but we can model that with a bipartite graph, right? And now maybe we want to find some kind of going off of the student and internship example. Maybe we want to find some kind of like global assignment that maximizes like everyone's happiness, right? We want to figure out who goes to what internship. A student can only accept one internship, and let's say every company only has like the space to hire one intern, right? So we want to match a student to a company in a way that like that maximizes like the total happiness or something like that, right? That's the idea of bipartite matching. I maybe I could have introduced this better, but it's whatever. Um, so maybe I'll define this better over here. Bipartite matching. I'm given a weighted bipartite graph. Choose a weighted bipartite graph, which I'll call V E W for the weights, and maybe U to represent the set of vertices on the left, right? Because I have to, bipartite graph means I have to be able to partition my vertices. Um, choose a set of edges uh, such that um, each vertex only has at most one edge incident to it. And sometimes we'll care about like the total weight of edges in E prime is maximal, right? So our example here is maybe there's like 4 students and 3 internships. Not everyone's going to get an internship. I'm sorry. Um, and now we look at like so these are students. These are internships, right? And we look at who applied to what. So maybe this first person only applied to one, right? The second person applied to all 3, and then each of the next 2 people applied to 2, right? Yeah, rip to whoever's not getting an internship. Um, I'm sorry, is this too real? Should I should I use a different example? Uh, maybe we can do like uh med students and like hospital residencies or something like that. I don't know. Um, anyway, so we have a graph here that represents like who applied to what, and maybe we can put weights on here that represent like the strength of their application. So maybe this was incredible. This is like 100, right? It was like a 3. It was like a 50. It was like a 20, right? And this is like a 60. It's like a 30. I don't know. I'm just, 75, 80, right? Something like that, right? And so now we want to um, a possible matching, right? Is we pick this edge, and this edge, right? This tells us that this student gets this internship, this student gets this internship, this student gets this internship, and this poor person doesn't get an internship at all. Um, the total weight of this matching is 3 plus 30 plus 80, which is 113, right? Can we do better? Almost certainly, right? We can match this one instead, this one, and maybe this one, right? That gives us 150 and 80, which is 230, right? So a bipartite matching gives us a pairing of students and internships that they applied to. A maximal weight bipartite matching or like a maximal bipartite matching gives us like the best possible pairing, right? So uh, you can imagine that this is maybe a problem that people would care about, or a problem that you could use to model like a real world thing that you might care about, right? Um, okay, so I'm going to quickly jump. I'm going to cut to the chase here, right? So I'm going to say we can use Ford Fulkerson for bipartite matching, right? The way that this works is we think of each edge that we've picked as an edge that we've saturated with flow, right? So we want to frame this as a problem of finding flow, or as a problem of finding a maximal flow. Um, The constraint, of course, is that every vertex can only have one edge incident to it that we've saturated, right? So like if all we try to do is, I mean, first of all, Ford Fulkerson doesn't apply on this graph, right? Because we need a source and a target. Well, let's say we add a source and we add a target, right? It still doesn't apply because there's nothing stopping Ford Fulkerson from saying, okay, this vertex is going to push 3 units here and 50 units here, right? That's perfectly fine. So we need to stop that from happening. And the way we can do that is by adding a bunch of virtual vertices, right? Um, so we can add, I'm going to draw these in orange, right? So we'll add a vertex here, a vertex here, here, and here, 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 and here. So one for each of these, and there's going to be a single edge going along these, right? And then we're going to, of course, have our source and our target. So here's a source, and here's our target. Um, and we can put weights on here, or we can put capacities here that sort of, um, I mean, we can just put a capacity of 1, right? So as soon as a unit of flow is pushed along here, it's necessarily not going to be able to grab anything else because we're only working with integers. Oh, I guess that's another theorem that if all of the weights are integers or if all the capacities are integers, then the maximal flow is always going to consist of integers along each edge, right? And now if we just run the algorithm and find a flow, the flow is necessarily going to give us like some of these edges are going to have flow along them. Maybe not all of them, probably not all of them, but here like 3 of them are going to have flow, right? Um, and then because there's only one unit, only one of the outgoing edges can be picked, and then these will have flow that collapses back into T, right? And so the output of running Ford Fulkerson is going to give us a sort of uh, it's going to pick a set of edges for us, and that's necessarily going to be a bipartite matching, right? And we can mess with the capacities to make it maximal, or we can like use these capacities to make it maximal. Okay, it's 9:40. Um, you're free to go unless there's questions. I'll probably talk more about this tomorrow. I'm also going to post the exam and give it give yeah, I'll make a Piazza post with exam information. Any questions? You can ask questions about the final with the caveat that I might choose not to answer them. Do you have a question now, or do you just mean in general?